Can a machine learn a completely new task simply by reading a few examples, effectively reprogramming itself on the fly without changing its internal code? This capability, known as in-context learning, challenges the traditional paradigm of how artificial intelligence adapts. In-context learning is the capability of models to generalize based on specific examples provided in their input stream. Crucially, this process happens without a single gradient update, meaning all adaptation occurs strictly within the forward pass of the network. To explain how this works, scholars propose two complementary mechanisms. First, the model may simply recognize a skill it already possesses using probabilistic inference. Alternatively, it can actively learn a new skill by running an internal process analogous to gradient descent. Understanding these mechanisms requires looking at specific scaling laws. We distinguish between context scaling, where adding more examples helps transformers improve, and task scaling, which depends entirely on the diversity of the original pre-training data. Now that we understand the mechanics, let's examine how this paradigm is reshaping practical applications and downstream tasks. These scaling properties have enabled remarkable breakthroughs, from processing hundreds of thousands of tokens in many-shot scenarios to extending capabilities into non-text domains like molecular biology. Recent systems can even optimize their own prompts using reinforcement learning. However, this power comes with theoretical caveats. While in-context learning rivals optimal estimators in few-shot settings, it faces unexpected inefficiency in long contexts, sometimes requiring up to 45% more demonstrations than a perfect learner. In-context learning represents a fundamental shift in how we build adaptive systems, moving us from static weights to dynamic, prompt-driven intelligence. For more on this evolving field, visit emergentmind.com.